if you attempt to design and tune our regulator initially, we can decouple the voltage reactive power loop and the active power frequency control loop. And we can, if we introduce very simple controller, we observe that we need kind of large gain to fulfill the steady state requirements. However, sorry. Sorry, not that. The high gain gives poor dynamic performance and stability problems. So we need a slightly more complicated controller to fulfill the requirements. Something that is similar to a PI controller, a PID controller is sufficient. And what you could have in mind is that if you use a PID controller, and you have seen from the literature that there's something called a transient droop, then you should know that the transient droop that appears in those governor models is actually corresponding to the inverse of the proportional gain if you have a PI controller. With a PI controller, that would be Kp. With the other structure, it would be 1 over this transient droop, more or less. So, alternatively, we also saw that for many of these control systems, and that's the point here, that they introduce an internal feedback with the aim of reducing the gain in the critical frequency area. So the internal feedback in this respect with the derivative term. But as I said, as I pointed out, that a proportional controller with an internal feedback of derivative type is somewhat equivalent to a PI controller with a droop feedback. So what I'm writing there is that these two control structures are equivalent. It's something to remember. Okay, I have some comments on frequency control, frequency stability in the power system, from a power system point of view, when you talk about large systems. So some textbooks talk about when you discuss frequency control, frequency stability, they talk about different stages of response. And these are just summarized here. I mean, the first thing that happens if you have a disturbance is that you get rotor swings in the generator. That's what we talked about yesterday. The other thing that we don't see unless we have model several generators and we go away from the infinite bus framework, is that you have, for any disturbance, you will have a frequency change. It says frequency drop here, but that refers to the case, of course, when you have a loss of generation or you have a load increase. So what happens when you have that kind of imbalance is that the frequency drops or it increases, and the rate of change of frequency is very much related to the inertia of the total system. So the inertia of the total system is very often referred to as the sum of the H constant and of each generator and the installed capacity of each generator. Here to n generators. That is can be measured, for example, in gigawatt seconds. That tells you something about the strength of the system with respect to inertia. And then, of course, there is a certain average here. If you considered the H constants to be in the same area, you could say, for example, that it is the average H times the installed capacity of the system. Gives you an idea. So its average H is 5 seconds, and the installed capacity is 100 gigawatt, and 500 gigawatt seconds would be the effective inertia. This is sort of the uncontrolled system, but at some point the primary control starts to be active, and then we are at sort of stage 3, where we have the primary control, also in sort of European terms called frequency containment. And then the fourth stage is the secondary control, referred to as frequency restoration, which is the set point control, when you adjust the set points. And then, of course, you could have to talk about tertiary control, unit commitment, and economic dispatch, but that's sort of usually manual operation, so operator initiated. So this is my picture of this. I haven't sort of depicted the rotor swings, but when there is a loss of generation, for example, the frequency would drop. The rate of change of frequency is related to the inertia. Then you have the primary reserve activated by primary control, which contains the frequency at some level depending on the droop of the system. And the droop of the system or the sum of the droop of all the generators results in a system frequency response in terms of megawatt per hertz. And that is a useful number to know, at least for the transmission system operators in the Nordic country, that relate very much to that number. For example, the minimum requirement I have is that this should be a minimum of 6,000 megawatt per hertz. So if the frequency drops by 1 hertz, there must at least be 6,000 megawatts that is activated. And this is a system of maximum load around 50, 60 gigawatts. So 10% of the installed capacity, something like that, should be available for primary control. Primary control is activated as a function of the frequency drop. And then in order to restore the frequency to 50 hertz after an imbalance, the secondary controls are activated. But these are slower, sometimes even manually activated. But they will then restore the frequency. If these are not working, then the tertiary control will be activated to do that job. Okay, that's the basics. Here now, when we talk, since we're going to talk about phaser measurement units and wide area monitoring and through control system, this is a picture from a prototype that we made at the Norwegian transmission system operator at Statnett. I don't need that now. So this is depicting a number of phasers in the Nordic transmission system from north to south. You see, for example, that the phaser, the voltage phaser in the northernmost transformer station is leading the one in the southern Norway by almost 90 degrees. That is due to the characteristic of the Nordic system, of course, with the long distances from north to south. But what I wanted to show with this is that you can, if you measure the frequency by phaser measurement units, you can see all these stages. You see the power swings here. You see something that there are swings, oscillations in the frequency at the same time that the frequency is dropping. So you can say that here you see the power swings, and you see the frequency drop, and you see the activation of primary reserves. So stage 1, 2, 3, and if we look at it in a longer perspective, this was the original window we looked at. You see that there is a certain overshoot, but the frequency settles here, so you have a steady state deviation which is slowly being regulated by the secondary controls. So that is one benefit of that we have illustrated, one benefit of phaser measurement units, that you are able to see more details of characteristics in the power system. The frequency containment and the primary control is very much related to the fact that we have proportional controllers, in steady state proportional controllers. The droop, the steady state gain, is called the droop because it activates power as the frequency drops, right? If the frequency drop, you will have more power, so we can draw the line frequency versus power, and the slope of that line will be the droop, and the inverse will be the controller gain in a way. It is in this picture is indicated by two different lines because that is because of the requirements in the Nordic system. The generators are required to provide a certain amount of primary reserves down to when the frequency is 49.9 hertz. After that, they can relax. They may relax somehow the contribution, but they need to provide a certain what you call FCRD for disturbance reserves. I mean, within 49.9 and 50.1 hertz, we call that's the sort of the normal operating range where the frequency is allowed to vary. So we distinguish between that and when the frequency is outside, when there is most likely a disturbance happening. But again, this is from a controller's perspective, I mean, if this is in per unit, that is sort of what you need to know in order to calculate the frequency response of your generator. And of course, if you take into account that Fn is 50 Hertz, and that is in if you the droop in percent is 100 times here you have that delta P over delta F is like right there, 2 Pn over given in percent. That's an easy formula to if you compute how much reserve you have, you need to add up that number for all your generators. So if you do that for all your generators, you have the system response in megawatt per hertz. That's something that the operators want to know. Okay, that's basically what I wanted to say. We'll come back to that with the applications later. But that's just to have mentioned the most important terms. I'll say a few words about the power system stabilizers, not too much. But coming back to this, to the block diagram that we started with, even though we designed controllers based on sort of decoupling of the loops, there are indeed couplings between the loops, and that coupling can be also utilized for control purposes. And one of those couplings that we utilize is when we design power system stabilizers. We have some power outages here, I think. So let's just wait. maybe you need to restart this. I think it's coming.
Today, I can see it.
Yeah, it's coming now, I think. Maybe not. Should we cancel it? Maybe now? Yeah, it works now. Yep, we're back. Yeah. 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 So the couplings due to the interaction between by the electromagnetics, we have couplings which can be utilized. This coupling can be analyzed in different ways. I won't go into that, but if one thing that I tried to show yesterday was that there was damping. I mean, the loop from here down to the electrical power actually provided some damping. However, the AVR to some extent tend to cancel, in the sense that very often the AVR acts acts against damping. It's actually sometimes oscillatory modes. But there is a natural damping through this loop. So if one can design a controller so that it actually add damping through here, then we have a good solution. And that's what the power system stabilizer does. Without going into the detail here, you could show by the transfer function that it is so. So what one then want to do is to add a modulating signal to the AVR in the correct frequency range and with the correct phase lead or phase lag, so that it actually add damping at the certain frequency that you want to add damping. So this is a much more sort of difficult controller to comprehend, because we are not interested in controlling a specific variable, but we want to control this variable at a certain frequency. And so we need to find an input signal, and that is a good indicator of this oscillatory mode, and run it to a controller, a phase compensator, to give the correct influence. And that controller it's quite easy to show that the best measurement from that is ideally the speed of the generator or the frequency. That can somehow be shown in this graph, which tries to depict how the phasors in frequency, and the understanding here is that these are the phasors that is observed, and that is how they move at the frequency of that oscillation. Consider oscillation in the time domain. Maybe you have 1 hertz, so we could say that this is 1 second, 2 seconds. So in this picture, you might say that okay, if you have two variables here, you can depict one as this is a phasor of this one, and the other one is lagging like 80 degrees or something. So it would be depicted as something like smaller amplitude. Do it again. Let's say that this is a speed, and it's very seriously undamped. This is omega. Then like that. So this is delta, this is omega. In the phasor diagram, if we denote this as the omega phase, no. Again. This is omega. Then the delta is lagging 90 degrees, right? Because if we consider these as phasors, omega comes 90 degrees ahead of the angle. And that angle is just the integral of speed. So that is what depicted here. So, and that means that if we are going to damp the frequency, we need something in here that is actually in phase with the speed, because then it comes in as a minus, so that will counteract the speed variations. So that is why this is called D, because essentially, if it's in phase with speed here, it will act damping. Now, if we look at the phasor of the EQ dash, well, how that is behaving, it is essentially partly in phase with speed and partly in opposite. It has its phase around here. And you can convince yourself, looking at the responses, that EQ dash might very well be in phase with the delta, so that this adds damping. However, the input from here may be counteracting. So our aim is to make this transient internal voltage move in phase with speed. If we can make the transient voltage vary in phase with speed, we have a damping. So that is the objective of the power system stabilizer, to sort of modulate here so that the exciter is in phase with speed. This show that in more detail. If we decompose the internal voltage, you have one phase in phase with speed, one phase that is in opposite. The exciter moves it a little bit, but we want it to move in this direction at that frequency. How do we do that? If, for example, we have access to speed measurements or good frequency measurements, we take that signal through a band pass filter, first a low pass filter to get noise out of it. We put it through a high pass filter to take away the offsets, the mean value. So we have a signal that has a mean around 0. So we maintain sort of, we exclude as possible of the frequencies that are not relevant for stabilizing. We do that with a band pass filter. And then we need to have a phase compensator to make sure that our actual response is in phase with speed. And this is the difficult part in PSS design. And then, of course, needs to be a gain, certain gain, and some limiters. But tuning the phase compensation, that's the difficult part when you're working with power system stabilizers. If you look into the literature, if you look into what are the available models in the simulators, you will encounter the type called PSS2A, or versions of. In practice, perhaps the most widely used PSS, and the strength of it is in its input, because it measures speed and it measures power. And the output of that block is a signal that is a good representation of speed or frequency. The reason why doing that is that it may be difficult to measure speed or frequency at high enough frequency. So this is a way of getting a more clean signal out to the controller. But what you should be aware of, the PSS is just the same. You have a phase compensator here and a capacitor as, but there is slightly different. But this is now we could have more used in here, but the conclusion would be that the output is a good representation of speed or frequency. So what do you do then when you design stabilizers? Well, of course, first you need to know what are the problem, what is the problem, what are the low damp modes that you want to stabilize. So ideally, of course, you would like to do eigenvalue calculations and identify the most critical modes. If you are out in the field, of course, you don't maybe not have access to that type of models, but you can based on some measurement, you can identify that frequency. And then ideally you would want to do calculations of observability and controllability. Where do you observe this mode best? Where is it best controllable? And you can do that by computing observability factors, controllability factors, participation factors, or transfer function residues that are very similar. Indicators that we can come back to. I mean, but that it would be if you have a choice of where to install your stabilizer. Then you would go for the place where it has most efficiency, of course. Having decided the locations, then I would do a frequency response calculation. Calculating the frequency of your plant so that you can design your controller. And then you might want to, if you are sort of advanced on power analysis, you might want to compute, for example, transfer function zeros to see if there is some problems. If you have a transfer function 0 close to where you have the dominant pole, then it might not be effective. Poles turn to approach zeros in a closed loop setting, so zeros can be troublesome. The solution then is to move to another site. That was essentially what I wanted to say about stabilizers. Again, we can come back to that later on if you have time, related to the applications later. So when did we start that? Do you remember? When did we start? Did we start 2:30? Okay, yeah. So because I just wanted to see whether we should have a small break because before I embark the final subject, but I will start the introduction anyway. And the introduction is now we're sort of moving from having our focus on a single power plant, control and impact on the power system, to the large large-scale power system with the hundreds or maybe thousands of generators. Then we need to have in mind that these are large, complex, hundreds, thousands of components, all with their dynamic characteristics. They're mostly the system is characterized by distributed control, single control loops. There are very little sort of system-wide controls in the power system. The controllers measured locally and controlled locally. The only sort of common reference in an AC power grid is, of course, the frequency. But it's measured locally still, but it is a global indicator of balance, of course. Low frequency oscillations, however, when we talked about the natural frequencies of one generator against the grid, that is one type of oscillations. But when when the number of generators starts to oscillate in phase, and maybe in counterphase with generators in another part of the system, we talk about inter-area power oscillations or system or system-wide wide modes. And of course, these system modes or inter-area modes, they can be critically low damped, and they impact the performance of the power system in sense that they may limit available power transfer capacity on certain corridors, as I will demonstrate. So it is of interest to provide as much damping as possible to those, of course. And what are the issues here when we try to analyze this? That the main tool we have is simulators, non-linear simulations like PSSE, Power Factory, whatever they are called. And you simulate and you can observe things, and you try different things, and you observe different things here and there. You see that there is a problem, but you don't know you don't know much about the nature of that problem, or what causes the problem, or where is this observable or controllable. So that results in a lot of trial and errors. So for systematically analysis and controller design, of course. We want to identify the problem, assess the critical modes, know about the observability, know about the interaction and controllability. And if we want to do that, we have to go to linear tools, linear systems, because that's where we have the powerful mathematical tools for it. So modal analysis, small signal stability assessment is the tool. And then the question is and the analysis. So if we talk about modeling, in such models, you usually have various classes of generator models that you use. What we started out with today or yesterday was basically the third order model, but in many cases you would use a fifth order or a sixth order model in these simulators. The two other differential equations here are representing the damper windings in the generator. So you see, you already here have 5 or 6 state variable per generator. And this must be connected to the grid, and then well, it follows the same approach that what we did this morning, by identifying the transient or sub-transient voltages and the current components for each generator. But we need to link that with the total model of our grid. It's an algebraic equation. Equations. At least it's the linear version of the admittance matrix that relates voltages to currents. So if you know the current injections at all nodes, we can compute the voltages at that nodes. Okay, that's what you learned about power flow. Is how to establish the admittance matrix for the entire system, consider generators and loads as current injections, then you know the voltages. And then you need them to decompose these currents to each generator in order to compute the electrical power. And when you have decomposed the currents, compute the electrical power, well, then you can update the differential equations for each generator. So this is the complexity of a large-scale dynamic simulator. Have a mix of algebraic equations and differential equations. Have different references. If you have salient pole generators, you have your d-axis or q-axis will be different from each generator, so we need to try. And you end up with a flow chart like this for system simulator, like PSSC, Power Factory. You set the time, you run your some events, whether that is slow change, slow and when you completed step all of the differential equations for the generator. If you have a 5th-order model with 5 or 6 differential equations for each generator, and in addition you have all the controllers and everything else, that's differential equations. Then you do a numerical integration, one time step. Go ahead one time step, update your internal voltages of the generators and delta so that you can go to the next time step. And you simulate step by step. Sometimes you interrupt the simulation to do some changes, like tripping a line, changing a load or something. But this is the way. And of course what you end up with is maybe I should write it the other way around, more common. Up with low. equation. Do the analysis, you must transform, linearize, so that you have that on a form. And where you have eliminated the variables by where you have limited y from this stationary equation. So y can be expressed as function of x in u. So that is, I don't recommend that you start doing by yourself if you have a model with 100 generators, but the computers can do it, right? So they will be able to come up with this model are down to the basics of this. Now, the question is what need to know what an eigenvalue is or an eigenvector. Then we have found an eigen. Now, if this matrix has rank, and we do have W is equal to the same times the eigenvector matrix where this is where this is lambda 1 to lambda n. So that's the eigenvalue transformation, and that you define a new variable z such that x is w times set. And or similarly, set is I think I've used the letter u, yeah, for the inverse times x. So w is the inverse of u and vice versa. This is the right eigenvector, and this is the left. That's how it is. And the nice thing then is that if you do the transformation, and you apply and you use the definition W set plus VU, and this is W set derivative, and you multiply everything by U because that's the inverse. Then you get UW set dot is UAW Z plus UVU. This is identity matrix. So we have set is U times A times W, which per definition, you see, so this is the main strength of model transformation. One eigenvalue. And you solve the differential equations for such a system, because when you have, you can always, each of these you can solve by itself because it's diagonal. And then since x is linear with solution that is order differential equation, you know that really interesting is that the eigenvector itself, it appears as sort of a gain factor in the solution, so that you could say that call it the mode change. understanding how things oscillate at different frequencies. As I should show this. Total response is then appears as a sum of all these responses from each one of them by one eigenvalue and one eigenvector. So the basic two for smaller systems, easily computable with thousands of state variables. It is very time-consuming to compute eigenvalues. So you need some iterative schemes often, which the simulator often have nowadays. And then, having computed the eigenvalues, identifying which of them are critical, you can compute the sensitivity factors. Just want to remember that X is W. And what are our X's? Maybe delta 1, delta n, omega 1, omega n, EQ dash 1, EQ double dash, and so on, controllers. Hundreds or thousands of state variables, and these are the, on the right side is the modes. It's set 1 plus set uppercase n. Have here, if we look, for example, at speed. And remember that if set number I is sort of the critical mode, because it corresponds to eigenvalue number I, which is minus 0.01 plus J3, for example. Okay, what we do, we look in that column, and for example, look at the eigenvectors formed to that mode. Then we have computed the mode shapes mode. In the same line here that is exactly 0, it's a bit to control that. So the left ability. The end of the day, or maybe we have to do like last time that we restart escape. Yeah, I'm just finding that. Yeah, it didn't work last time. I'm not ready yet. I can fix it. Oh yeah, it was not working yet. I thought I saw the screen. Maybe now? Yeah. No, it works. Did you have to stop the program and restart it? That was? Yeah. Because it was trying and then we had to stop it. To try again. And -1. Secure, yeah, at the moment.